This is part 2 of our lecture on section 1.4, the matrix equation AX equals B. And in this part, we're going to define exactly what that equation is, look at an example, and make some observations about what the meaning of AX equals B is. So to get started here, let's just state again that if A is an m by n matrix and X is an n by 1 column vector, then the product AX is an m by 1 column vector. We saw that in our previous video, the part 1 portion where we worked through an example. So let's just note that if A is m by n, and if X is n by 1, and in fact the number of columns of A has to match the number of rows of X. So these, we want to say, must match. And what I want you to realize is there's no mystery to where this product vector comes from. It's almost like the n's cancel out, and we end up with an m by 1 product. So X is in Rn, an n-dimensional column vector, but the product AX that we get is a column vector in Rm. And with practice, we'll get used to this fact. It won't seem quite so mysterious. Now, let's go ahead here and move this up a bit. And again, let A be an m by n matrix. So m rows, n columns, with columns. I'll denote the columns of A as A1, A2, to AN as column vectors, right? We're going to let X equal a column vector X1, X2 to Xn, and think of the n entries of X as being variables, just like the x1 through xn variables that we use in our systems of equations. Now, let's let B be a column vector in Rm, and the m entries of B are numbers, so constants, real numbers. I realize I should put a line over my X right there because that's a column vector. Now we can state theorem 3. The solution to the matrix equation AX equals B. So we think of that as an equation that has a matrix, a column vector, and another column vector with variables, with unknowns. So solving this equation means finding values for x1 through xn. So the solution to the matrix equation AX equals B is the same as the solution to the system of equations whose augmented matrix is the following. It's a matrix with the following columns. So I'm just going to list the column vectors. A1, A2, to AN, the columns of the matrix A, but with something extra, with the column vector B on the end. So let's put a box around this, because this is something we're going to have to talk about for a while and get comfortable with. So there's our statement of theorem 3. Now before we work on that a little bit, I just want to make a note here. A all by itself, which can be written using column vectors as A1, A2 to AN, A by itself is not the augmented matrix. We need to include that column vector B on the end in order to get the augmented matrix for our system of equations. Now, in order to bring theorem 3 to life a little bit, we're going to look at an example. So there it is. Let's go ahead and start working on an example here with an actual matrix A. So I'm going to let A be the following matrix: 2, 1, negative 1, 0, 4, negative 2. It's actually a 2 by 3 matrix. So I just picked this out ahead of time. We're going to let x be the variable vector, so it will have variable entries, x1, x2, x3. That's actually a 3 by 1 column vector. And B, I just picked a vector to be B. It's going to be the column vector 2, 3. B is a 2 by 1 column vector. Then AX equals B looks like this. So let's try to bring this matrix equation to life a little bit. Now the matrix A, I'm just going to recopy here, is 2, 1, negative 1, 0, 4, negative 2. I'm going to multiply the matrix A times x1, x2, and x3. And in order to be able to do that multiplication, I need the number of columns of A, which is 3, to match the number of entries of x, which is also 3. So this 3 has to match that 3 for this multiplication to be even possible. And I want that to be equal to the column vector 2, 3, which is actually just a 2 by 1 matrix. when I multiply A times X, I'm going to end up with a 2 by 1 column vector. And to see that, let's go ahead and go through this matrix multiplication process. Now, we did an example of this in our previous video for this section. I take the entries of X, so I'm going to take X1 times the corresponding column of B, so times the first column, 2, 1, plus I take X2, the second entry of X, times the second column, negative 1, 0, second column of the matrix A, plus I take the third entry of X, X3, times the third column of the matrix A for negative 2. And we want that to be equal to B, the vector 2, 3. Notice I have a sum of column vectors with 2 entries here equaling a column vector with 2 entries. So the dimensions are matching up in the right way. Now let's go ahead and do my scalar multiplication. I have to take 2 times x1 over 1 times x1 is x1 plus negative 1 times x, negative x2. 0 times x2 will still just be 0 plus 4 times x3 over negative 2 times x3 equals 2, 3. And now I can add the 3 column vectors on the left-hand side of the equation to get the column vector 2x1 minus x2 plus 4x3 is its first entry. Second entry is adding across the second entry is I get x1 plus 0 minus 2x3 equals 2, 3. So notice I have a 2 by 1 column vector equals a 2 by 1 column vector. They can only be equal if their corresponding entries are equal. So this equation means 2x1 minus x2 plus 4x3 equals 2, and x1 minus 2x3 equals 3. That's actually a system of linear equations. Solving the original matrix equation, which we called AX equals B, sorry, went off the bottom here, let me move that up a bit, is the same as solving this system of linear equations. Now, pretend for a minute that we didn't even have this matrix equation to start out with. Suppose we just started with this system. How would we solve? We would set up an augmented matrix for the system. And that augmented matrix would consist of first the coefficients of x1, right, 2 and 1, then the coefficients of x2, negative 1, 0 from the second equation, then the coefficients of x3, 4, negative 2, and finally in the augmented matrix we put the constant terms on the right, 2, 3, and we would row reduce this augmented matrix. But notice that this augmented matrix is exactly the same as the columns of the matrix A along with the column vector B written alongside. That's just what theorem 3 says that we just wrote down in our previous page of notes a moment ago. This augmented matrix here, this notation here at the bottom of the red box, is the same as this augmented matrix here. So solving a matrix equation means solving a system of equations, and we could have gone right from here to the augmented matrix to reduce the augmented matrix and find our solutions quickly. I'm not going to actually solve. I'm going to actually stop at this point. So we won't actually solve this one. We already know how to do that, so I'm going to leave that example at that point. Now, there's a little bit more I want to say in this video here to kind of sum things up. And this is sort of the point of what we've been doing here. We see that we can now compare a matrix equation that has the form AX equals B. We can compare that to a vector equation and the vector equation is x1 times a1, the first column of A, plus x2 times a2, the second column of A, plus all the way down the line xn times an equals B. That's really the same idea as the matrix equation. We've just carried out the multiplication of the column vector x times the matrix A. So this vector equation solution is the same as the matrix equation solution, which is the same as solving a system of linear equations. And how would we do that? We would solve the system of linear equations by setting up the augmented matrix A1, A2 to AN using the columns of A along with the vector B. So we see that I would say we have three different ways to say the same thing. And before we finish, one more observation here. Write this as a notice. I'm going to bring in a little bit more of the vocabulary we have. We've developed AX equals B has a solution if and only if B is in the span of the columns of A, of A1, A2 to AN. So there we brought in our idea of span of some vectors. Box around that. And just one last comment, another way to think of that is B is a linear combination of A1, A2 to AN. That's just another way of rewording that statement about the span of A1 through AN. Now that's most of what we need to know in section 1.4. We have one more video to come that's going to be a little bit more abstract, a little bit more theoretical.